need to find value p. Now p is equal to the limit as n goes to infinity of the absolute value of the nth plus 1 term over the nth term. So that's the very first thing we need to do in order to come to the ratio test. Now there are 3 conditions of the ratio test. The first condition is if p is greater than or equal to 0, but less than 1. In this case, then our series converges absolutely. The next condition is a divergent one. This occurs if p is larger than 1. If p is larger than 1, or p equals infinity, then our series diverges. Now our third and final term is if p equals 1. In this case, we don't get any information from the ratio test and need to figure out if the series is convergent or divergent through other means. If the nth plus 1 is larger than or equal to 0 and smaller than or equal to bn for all n greater than or equal to 1, and the limit as n goes to infinity, b of n equals 0, then we know that the series above converges. Let's take the series 1 over n squared to infinity, starting at n equal 1 of 1 over n squared. So this obviously converges, right? If you just take the limit of this, 1 over n squared, you see that this equals 1 over infinity, which equals 0. Like, this obviously goes to 0. This converges. However, this returns an inconclusive ratio test. So remember, we have to find p, which equals the lim as n goes to infinity, the absolute value of a n plus 1 over n. Okay, so in this example, we plug in 1 over n squared, right? So we have 1 over n plus 1 squared over 1 over n squared, okay? That's equal to n squared over n plus 1 squared, which equals n squared over n squared plus 2n, plus 2n plus 1, which equals infinity over infinity. Oh, and I should have mentioned, I meant to write the limits here. So it's the limit as n goes to infinity at each of these points. And so the limit as n goes to infinity of this, n squared over n squared plus 2n plus 1 equals infinity over infinity, which equals 1. P equals 1 means that the ratio test provides no information. However, this does not line up with the fact that this is still an absolutely convergent series, as you can see here. In order to determine if this series is convergent, we first need to set up the ratio test and then simplify all this. So in order to set up the ratio test, let's find p. P equals the limit, in this case is I goes to infinity, the absolute value of a n plus 1 over a n, which in this case is -1. Okay, so now that we have this all set up, we need to simplify it.
The first step for this is to divide the fractions and then apply the exponent rule. So we get -1 to the I minus -1 plus I. This is times 3 to the -1 plus I times x to the 1 plus I. This is all over 3 to the I times x to the I. So now we get, just to keep simplifying, over 3 to the I, 3 to the I, x to the I. Now we apply the exponent rule, so we get -1. Let's see, -1 times 3 to the -1 plus I, x -1, I minus I plus 1, over 3 to the I. Simplify this again, we get -1 times 3 to the -1 plus I, times x, over 3 to the I. Apply the exponent rule again, -1 times x, over 3 to the I, minus 1 plus I. Okay, then we simplify again, -1 to the x,
Over 3, so we get negative x over 3. Okay, so now all that's done, and then we need to plug this back into our p. So p equals lim, I goes to infinity, absolute value, never. Okay, so this value has to be greater than or equal to 0 and smaller than 1. So since it's a limit of a constant, so we can plug this just directly in. Let's say that x is positive. And if x is negative, so these are the two conditions. If x is so if you combine these two conditions together, x needs to be larger than -3 and smaller than 3, and this series will converge.